Before we get into reverse engineering, we need to spend some time discussing the CPU, the central processing unit, and its architecture. Let's start by discussing, at a very high level, how a CPU works. Let's begin with a sample program, any program, and let's assume that that program has an icon on the desktop of your favorite operating system. This program is stored in secondary storage, that is, your hard drive. A common way to execute that program would be to double-click the icon. This in turn causes the operating system loader to take that executable from disk and move it into primary memory, or RAM. In addition to loading that program, it also brings along any resources that that program needs. Once that program is loaded into primary memory, the CPU can take over. It is notified of the entry point of the program, and it can fetch the first instruction out of memory. Once that instruction is fetched, it is then decoded and executed by the CPU. This in turn provides the functionality of the program, and this process repeats as long as the program is running. CPU architecture and assembly programming can become a deep and complex topic. Fortunately, you don't have to become an expert in order to be an effective reverse engineer. In this course, I'll introduce you to what I consider the essential elements to ensure the time you spend is as efficient as possible. As you just learned, the CPU is responsible for executing instructions. It is actually the CPU core that is responsible for this. Originally, CPUs had just a single core, and this limited performance, as it could only execute a single instruction at a time. With modern CPU architecture, now systems come with multiple physical cores, and it's not uncommon to see 2, 4, 6, or even more physical cores in a system. Virtual cores are also possible. An example of this would be Intel's hyper-threading technology. And while these don't provide the same level of performance as a physical core, they still increase the capability of the CPU. While this is essential background for understanding CPU architecture, it is relatively uncommon to have to deal with these cores when reverse engineering binary programs. And finally, there are CPU clock speeds. This number indicates the number of instructions a CPU can execute per second, and you'll oftentimes see this measured in gigahertz. As central as the CPU is, there are other important components, such as the network interface cards, secondary storage, your primary memory, and graphics processing units, or video cards. All of these play a role in system performance and capabilities, and we'll continue to discuss their importance throughout this course. Before we get into the ones and zeros, it's important to understand the different layers of memory that is available to the CPU, and where it goes to fetch instructions. First, we begin with the CPU registers. These are the lowest level of memory and provide the quickest access time. We will be discussing these in detail next. After that comes caches, and these caches sit between the registers and primary memory. Primary memory is also considered your RAM, or your random access memory. Next, we have secondary storage, such as your hard drives or network attached storage. And then finally, there are input devices. Keep in mind, the further away from the CPU that we get, the longer it takes to access content in that memory, therefore decreasing performance. When reversing software, you may see this, as program instructions favor to keep data in registers versus using other layers of memory. 32-bit systems are generally considered to have 8 general-purpose registers. And you can see those 8 general-purpose registers depicted in this table: EAX, EBX, ECX, EDX, ESI, EDI, EBP, and ESP. With some registers, it is possible to directly reference different sections of that register. For example, if we wanted to reference the lower 16 bits of the EAX register, we could use AX. This one further can be broken down, and we can reference the lower 8 bits using AL, as well as the upper 8 bits using AH. You can see in this table that this is possible for EAX, EBX, ECX, and EDX. For the remaining 4 registers, you can only reference the lower 16 bits using SI, DI, BP, and SP. With 64-bit architecture, which is the more prevalent nowadays, it not only extends the 32-bit general-purpose registers, but it also adds 8 more. As you can see in this table, R8 through R15 are added to the registers available to the CPU. In addition, the 32-bit registers are extended to become 64-bit registers. For example, EAX now becomes RAX. Similar to our previous discussion, these registers can be broken down, and you can use this table in order to understand what components of any specific register can be directly referenced. You've probably noticed that certain sections of a register cannot be directly accessed. For example, the upper 16 bits of EAX. Even though they cannot be directly accessed, there are instructions that allow us to move data from lower sections of a register into those upper sections. Let's look at these registers now in a slightly more graphical way. Consider RAX, which is a 64-bit register. That means it can contain 64 ones or zeros. From RAX, we can reference the lower 32 bits, which would be EAX. And from EAX, we can reference the lower 16 bits, which would be AX. AX can be further broken down into the lowest 8 bits, which is AL, or the upper 8 bits, which is AH. At this point, you may be asking yourself, why so many registers, and what are their actual purpose? On 32-bit systems, they're generally considered to have 3 pointer registers. The first is EIP, or the instruction pointer. This one is crucial, as it tells the CPU where to go in memory to fetch the next instruction. Next is ESP. This is the stack pointer. This is responsible for keeping track of the top of the stack in memory. And finally, there's EBP, or the base pointer, and this is used in order to create the stack frame for a function. That is, the space on the stack that is used for arguments and local variables. We'll continue to discuss all of these registers throughout this course and get into much more detail. Very similar on a 64-bit system, we have 64-bit pointer registers. These serve the same exact purpose, except that they're 64 bits instead of 32. RIP is the instruction pointer, RSP is the stack pointer, and RBP is the base pointer. Next up, we have index registers. On a 32-bit system, this is ESI, which is the source index, and EDI, which is the destination index. Very similar on 64-bit architecture is RSI and RDI. These registers are commonly used for copy operations. A pointer, or memory location, is moved into the source index. Whatever data is contained in that memory is then copied to the destination index. And finally, we have E flags and R flags. These are 32 and 64-bit registers that will often represent the results of an arithmetic operation, such as a comparison or a subtraction, and also the state of the CPU. Some common values include the carry flag, the zero flag, the sign flag, the trap flag, the direction flag, the overflow flag. Each bit within these registers represents a flag, and instructions can be used to check if the flag is set or not. That is, if it's a 1 or a 0. In R flags, or the 64-bit version of E flags, the upper 32 bits are reserved. This image depicts the state of the flags using the WinDebug debugger. And you will oftentimes find yourself, when debugging a program, checking the value of the flags, and even possibly modifying those in order to change program behavior. Now that you've learned some of the essential elements of CPU architecture, we're ready to talk about the assembler and program segments and continue to deepen our knowledge of low-level architecture.